Today we shall discuss how to analyze delay at a signal control intersection. And that's an important measure to define the level of service at controlled intersections. Delay will depend upon how the vehicles are arriving and how they are departing from the intersection. As far as arrival process is concerned, there can be three types of arrivals. It can be a completely random arrival, where the vehicles are arriving randomly at the intersection. And this random arrival occurs when the intersection is completely isolated. Means that there is no other intersections in the vicinity of 3 to 4 kilometers from this intersection. The second is grouped arrivals, when the vehicles arrive in groups. And that happens when the upstream signal is located at a distance of less than 2 kilometers. In between these two, when the intersections are located at a spacing between 2 to 4 kilometers, then it's a mixed type of arrival. It can be a combination of random as well as grouped arrivals. Now let us assume that the arrival of the vehicle is deterministic. And let us also assume that the vehicle arrival is uniform. When I say uniform, it basically means the headway is more or less constant and the vehicles are arriving in groups. So if you look at the arrival with time, this is the arrival rate. Let us say Q vehicles per hour. This is the time and this is the arrival and departure. Now, departure from the stop line will be 0 during red time and it will be maximum during green time. So, if you make a, let us say, signal here that this is the red time, then you have green. So, departure here will be maximum during green time and then 0 during red time. Like this. This is red, this is green. And this is what we call the saturation flow, S. S will be maximum during green time and 0 during red time. There will be no departure. Now, this is the input to the intersection and this is the output from the intersection. Now, if you plot these arrival and departure on a cumulative scale, then it will be like this, that this is the time and this is input or output. So input will be like this, cumulative, and departure will be like this, that during red period there is no departure and then it builds up here and then touches this line of input and then again like this. That is your input output curve on a cumulative arrival and departure scale. Now this is red, this is green here, this total time is green. Part of this green is utilized by the Q to dissipate, and after this Q dissipates here, then arrival is equal to departure. Now there can be three situations. One is when, let us say this is Q, rate of arrival Q, and C is the cycle time, S is the rate of departure, which we call saturation flow, and G is the effective green time and Q is arrival rate. Vehicle per hour of green, effective green in second, cycle time in second. Now there can be three situations when this arrival in a cycle is less than departure in a cycle. Q into C. Q into C is the number of vehicles arriving during a cycle. S into G. G is effective green time. At the rate of S, S into G is the number of departures from the stop line that can take place. Now, this situation is called unsaturated. Unsaturated cycle. Like this, okay? When the departure rate or the queue formed during red period is not sufficient to consume the entire green time, then there will be some amount of green which is unsaturated. This is what we call GU, unsaturated. And this is the green which is saturated, GS. It's two parts. Second case could be when this QC is just equal to S into G. In that case, this line will touch the Q line at the end of the green. So there is sufficient Q in the approach to consume the entire green. That is just saturation, saturated cycle. When the entire green is saturated. And third could be when the arrival is more than departure. That is a situation which we call oversaturation. Today, in this session, we will discuss these two cases, unsaturated and saturated. And in the next part, I will tell you about oversaturated cycles. Now, how do we calculate the amount of delay to a vehicle in a under saturation condition? Under saturation condition. Let me draw this figure again. Now, this is red. This is green. Again red. Again green. So, in first case, this entire green is not saturated. A part of it saturated, and let us say this we call GS, saturated green. This is red time, R, during which there is no output. And if you want to find out the delay, you basically need to find out area between the input and output curve. Area between input-output curve is always the delay. So, input is this at the rate of Q, output is this triangle. So, find out the area of this triangle. Let us say A, B, C. D is another point here. CD is unsaturated green. Okay. Now, what is this time GS? Now, saturated green. When the traffic light turns green, the queue form behind the stop line will start moving, and it is not that the entire queue will dissipate immediately. So, other vehicles which are coming to the intersection, they will join the queue until the last vehicle in the queue comes to a stop line. So, that is the saturated green. Now, the saturated green, you can calculate that the vehicles which are coming during red period, let me say R into Q, all vehicles which are coming during red period in the approach, plus vehicles which are arriving during this saturated green period. They will also join the queue. And the rate of discharge at the stop line, that makes GS. That is the saturated green. How much time you need to dissipate the queue completely? That will be R into Q, number of vehicles arriving during red, plus number of vehicles arriving during GS, divided by rate of discharge. That is equal to GS. If you simplify this equation, you get GS will be R into Q upon S minus Q. Remember, Q is the rate of arrival, S is rate of departure. And it is always convenient to put rho is equal to Q by S. That is called the flow ratio, arrival upon departure. And if you substitute this value here, it will be R into rho upon 1 minus rho. That is the saturated green time. R into Q divided by S minus Q. That is the saturated green. And how much is this ordinate now? B, let us say this point is E, CE. How much it will be? It will be GS multiplied by rate of departure. So this is GS multiplied by S. That is the number of vehicles which are departing in time GS. Total complete Q. So area of this triangle now, area of ABC will be half into base is R, into ordinate, that is S into GS. S into GS. Put the value of GS here and you get half of R into S into R rho upon 1 minus rho, equal to R square S upon 2 into rho upon 1 minus rho. That is the total delay. Or you can say area of this triangle. You know all parameters here. You know red time from the signal timings. You know rate of discharge from the stop line. You know Q, rate of arrival. So rho is also known. Now, this is the total delay to all vehicles which are using the intersection. Our interest is to find out the average delay to an individual vehicle. And therefore, average delay will be D average will be total delay divided by total number of vehicles using the cycle. That is Q into C. How many vehicles arrive? That basically this Q into C includes this part also, where there is no stopping of the vehicles. Vehicles are coming and going. So Q into C, total number of arrivals in a cycle length C. And if you substitute or if you divide this and simplify this, it will be equal to R square upon 2R plus G into 1 minus rho. That is the delay. R plus G is the cycle length, rho Q by S, and if you again substitute this rho is equal to Q by S and simplify it further, you will see that this D average is 1 minus G by C square upon C upon 2 into 1 minus Q by S. This is the equation you will find in most of the manuals to calculate average delay because of uniform rate of arrival. Whether it is Indo-SCM or the highway capacity manual of US, British method, Swedish method, in all methods, the first term of delay is uniform delay. And that is the equation. That is how it is derived. Again, I will repeat, G is the effective green time, C is the cycle length, Q is the arrival rate, S is the departure rate. Let us take one example. You have an approach to an intersection and vehicles are arriving at uniform rate of, let us say, Q is equal to 400 vehicles per hour. And the departure from the stop line S is 1800 vehicle per hour of green. Cycle length is 140 seconds. and the green time allocated to this phase is, let us say, 42 seconds. What is the amount of delay, average delay to individual vehicle? Now, here you can put all these values. C is 140. So, D average is 140 multiplied by 1 minus G by C, that is 42 upon 140 square upon 2 into 1 minus Q is 400 upon 1800. How much you get? That is, so this will be 44.1 second. Average delay to a vehicle for this given condition at the intersection will be 44 seconds. Now, how much time this intersection, this green cycle or green phase remains saturated? GS. GS is, if you remember, R into Q upon S minus Q. R is C minus G, that is 98 seconds. So this is 98 multiplied by 400 upon 1800 minus 400, and this is 28 seconds. So out of 42 seconds, 28 seconds is completely saturated when there is a vehicle in the queue. Remaining 14 seconds is unsaturated, and that is this one, 14 seconds. So if you see, Q into C is less than S into G, because there is unsaturated cycle, unsaturated green here. Now what happens to this intersection if I increase this flow to 540 vehicles per hour? 540 vehicles per hour. Let us see how much is GS now. GS is 98 into 540 divided by 1800 minus 540. This is exactly 42 seconds. Completely saturated now. The entire green is saturated. So that is the case when Q into C. How much is Q? Q is 540 into cycle length 140 divided by 3600 is 1800 multiplied by 42 upon 3600. They are now equal. That is saturation. And if there is saturation, how much will be the delay? You can calculate delay here. Instead of now 400, you have 540. So in this equation, this remains same, C. This also remains C, G by C ratio. Now this is 540. So this will increase, 1 minus this will decrease, and therefore delay will increase by some amount. You can calculate yourself. So that is the situation when this line will touch D point. That is the case of saturation. That is how you calculate delay in a undersaturation and saturation cycle. So I stop here. In the next session, we will discuss how to determine delay when the signal is oversaturated.